Hi, my name is Jami Newcomer, and I will be presenting the last part of our project, which is the last part of probability. So this is the law of large numbers. The definition is the phenomenon in which the relative frequency of an event becomes a closer approximation of the actual probability or the theoretical probability as the size of the data set increases. So basically, the larger the size of data, the more representative the sample is of the population. So as you can see over here on our table, we have flipped a coin multiple times. As we all know, there is a 50% of us getting heads on a coin because one side is heads, one side is tail. So it's going to be 50%. Now in this case, we tossed that coin 4 times and we only landed on heads once. So when we were doing the experiment, our probability of heads was 25%. Now we know that it's a 50% chance. So 25 and 50, there's a pretty large gap between those two. Now, when we tossed the coin 100 times, we got heads 64 times. So the probability of heads was 64%. That's a little bit closer to that 50% number that we're trying to get to. When we tossed it 1,000 times, the number of heads was 582. So the probability of heads was 58.2%. Again, even closer to that 50%. And when we tossed it 10,000 times, the number of heads was 4,989 times. So the probability of heads was 49.89%. Very, very, very close to that 50%. So as you can see, the larger the size of the data set, so the more times you do something, the more likely you're going to get a percentage that is closer to that actual probability or that theoretical probability that you've figured out in your equations. Up next is why do we use experiments so much in probability? So probability, the point of it is to provide information about the likelihood that something will happen. When we use experiments, we use manipulatives to better visualize those probability equations that we're working on in class. This way you can help to better see exactly what is happening. It's important to know as well that these experiments are used in the real world every single day. Many professions use these experiments when they're trying to figure out probability. So meteorologists, for instance, use experiments when they are predicting weather patterns. They're trying to predict the probability of rain, for example. In epidemiology, the probability theory is used to understand the relationship between exposures and the risk of health effects. So this is actually the study to control health problems. This is very important in our society. These probability experiments are also used in politics and sports all the time. So there's a wide range of ways that you can use these experiments, and so it's important to understand how they work because it's very likely that you'll be in a profession or in real life instances where you'll have to use these probability equations. Technology is oftentimes used in a lot of these experiments, so it's important that we help to get you comfortable with things like graphing calculators that can help produce random outcomes. There's many websites and virtual tools that can help in constructing these experiments so that you can see what exactly is going on when you're trying to figure out the probability of something. It's also very important to understand the difference between independent events and dependent events. So in an independent event, Whatever happens in one event has absolutely nothing to do with what will happen next. There are several reasons where this can occur. So the first is when the two events are completely unrelated. And the second, it can be when you repeat an event with an item whose numbers will not change. So for example, the number on a dice will not change. So no matter how many times you roll a dice, those events will be independent of each other. When you flip a coin, those events are independent of each other because you will always have two sides to that coin. Another way that this happens is when you repeat the same activity, but you replace the item that was removed. So if you have a bag of marbles that has 10 in it, you take one marble out, but then you replace that marble and you do that event again, then that first and second event will be independent events because the number of marbles was always the same. It was always 10 because you were replacing it afterwards. So for the equation of independent events, the probability of two events, A and B, is equal to the probability of event A times the probability of event B. Now in dependent events, the two events are dependent of each other. So if the outcome of the first event affects the outcome of the second event. So an example of this would be if I take a marble out of a jar and don't put it back in, then I change the probability for the next pick. So let's say I have a jar that has 10 red marbles in it and 15 blue marbles in it. If I take out one blue marble and then the next time I go to take a marble out, I do not replace it, then my probability of getting a blue marble is going to be different because I only have 14 blue marbles in that jar instead of the 15 that I had previously. So as you can tell, those two events are dependent of each other. One event determines the outcome of the other event. So area representation is another part of probability. It's a way to determine theoretical probability. Some believe it is effective, but there are some limitations to it. It is really good in certain situations, especially when you're trying to keep track of two independent events. It's a great way to visualize theoretic probability and help to understand using these area models. So we're going to watch a short video that is going to describe how to build an area model, and I would like you to follow along and copy on your own piece of paper what this woman is doing for her area model, because after that we will be creating our own area model with our own activity.
In this game of chance, we have 3 buckets with marbles inside. Bucket number 1 has 2 red marbles, 1 blue marble. Bucket number 2 has 1 red, 1 blue marble. Bucket number 3 has 3 red marbles and 1 blue. The way this game works is that first we're going to select a bucket at random. Then, from within that bucket, we're going to select a marble at random. You'll win if you draw a red marble. And we need to figure out the theoretical probability of winning. This is an instance where we cannot use a counting tree. We have to use an area model. So first, we need to create an area model to represent the situation. Each bucket represents 1/3 of a likelihood of being selected, so we'll divide our area model into 3. And then we'll represent the individual marbles within each bucket. As you'll see here, for instance, bucket number 1 had 3 marbles in it, so I divided bucket number 1's 1/3 strip into 3 equal portions as well. Now we get to the more difficult math, where we need to figure out what is each marble's theoretical probability of being selected overall in this game. Or more accurately, what does each individual rectangle represent as a fraction of the total? So here's the process we'll use. First, we need to identify the probability that the individual bucket will be drawn. We've already done that. It's 1/3. Second, we need to identify the probability that the individual marble will be drawn from within that bucket. And then we're going to multiply those fractions together. Looking at the very first bucket, and looking at this first marble here, red, that individual marble has a 1/3 likelihood of being selected out of that bucket. So we're going to take the 1/3 likelihood of the marble, multiply by the 1/3 likelihood of the bucket, and figure out that that marble has a 1/9 chance overall in being selected in this game. You can also think about it in terms of drawing equal sized pieces. So in my freehand sketch down here, you'll see I divided it into 3 equal portions. And then I'm going to draw lines that match up with bucket number 1's division. I have red here and red here. You'll see that they divide up into 9 equal sized portions, so it's not a surprise that each marble is representing 1/9 of the probability. Moving on to bucket number 2. Bucket number 2 had 2 marbles inside, which means that each one has a 1/2 likelihood of being selected within that bucket. We're going to take 1/2, multiply it by 1/3, and come up with 1/6. Again, if you wanted to freehand sort of sketch the situation, we're saying that our red marble here, we draw up the straight lines, divides out into 6 equal sized portions so that the likelihood of that particular marble being selected is 1/6 of a chance. And finally with bucket number 3, which has 4 marbles, each marble has a 1/4 chance of being selected out of that bucket. 1/4 times the 1/3 chance of the bucket being selected is 1/12. To visualize that again, we can say that we have our bucket representation here, and if I were to divide it into the equal sized pieces as suggested by the bottom row, we'd see that each one is representing 1/12 of the overall whole. So what we need to do next is to catalog all of the individual probabilities for each marble, and then we're going to have to add them up. We need to find a common denominator for each one of these fractions. The common denominator is 36, which means that if we had drawn equal sized rectangles, we would have drawn into 36 equal sized pieces. So the next step is to add up all of our numerators, and then we find that the likelihood of selecting a red marble in this game overall is the fraction 23/36. Please use this strategy as you complete out your homework due for Monday.
Okay, perfect. So next we are going to look at our own activity. So here we're going to use masking tape, dry erase markers, plastic cups, and Starburst candies. First, you're going to get into groups of 2. So you're going to use your table partner. Then you're going to grab your cups, label one as container 1 and the second cup as container 2. Randomly choose 3 pieces of the Starburst candy and put them into container 1. Then randomly choose 4 pieces of candy and put them into container 2. Now remember, it's okay to have more than one of the same color. Using your masking tape, construct a large square on the surface of your table. And then using your dry erase markers, label the left column of the square container 1 and the top column of your square container 2. Use a dry erase marker to complete your area model by creating 3 rows and 4 columns, since there are 3 choices in container 1 and 4 choices in container 2. Now, fill in each box inside the area model using capital letters to represent each combination. For example, RY would represent choosing red first and yellow second. After you have completed all of this, you're going to move on to the challenge questions on the next page. So this would be your two containers. So you would color in the colors that you have in container 1, the colors that you have in container 2. So you're going to identify with the capital letters the abbreviations for these 3, and then over here do the rest of the possible combinations as well. Then after building your area model, identify the total number of possible outcomes there are in this scenario. Then you're going to identify one outcome with the probability of 1/12 if you have it, then 1/6, 1/4, and 0. So we're going to skip down here. Once you've completed all of that, brought it up to myself to look over it, or called me over to your desk so I can look over it for completion and accuracy, then you're going to go on to these challenge questions. So the challenge questions are, what is the probability of getting at least 1, and then insert a color of your choice. What is the probability of getting 0, and then again the color of your choice. One of the ones that you've had in one of the colors of the Starburst candies that we gave you. And then describe one way that you could change the scenario to ensure that every outcome includes a whatever color of choice candy. And then the last question is going to be, describe what you think would happen if you were to randomly swap the piece of candy from container 1 with a piece of candy from container 2. Would the outcomes change? And remember to collaborate with your partner. You will be turning in only one of these papers per the 2 of you. Okay. So, after completion of that activity, we would move on to simulations. So, an example of simulations would be when testing techniques of gender selection. Medical researchers need to know probability values of different outcomes, such as the probability of getting at least 60 girls among 100 children, assuming that male and female births are equally likely. Describe a simulation that results in the gender of 100 newborn babies. So for this example, for a simulation, we could flip a coin 100 times and let heads represent girls and tails represent boys. But who wants to do this? We want to do simulations that can help to understand what a probability of something is. That way we don't have to do something 100 times or 10,000 times. A simulation is going to help so that you can do it in a much quicker and concise way. So, common misconceptions of probability. One is that thinking that the actual relative frequency of an event will equal the probability of the event. So, for example, thinking that 100 tosses of a two-sided coin will be 50 heads and 50 tails. So, as you see, we've done a lot of different examples and activities with coins, and just because probability is 50-50 doesn't mean that in actuality that is the result that comes out. Another misconception is that probability is based on true fact. Probability is just a number that is only as good as the assumptions and statistical sampling methods it is based on. For example, presidential polls are unreliable to determine the outcome. So as much as we rely on probability to help us guess or estimate on a future event, just because a probability states something will happen does not mean that that is exactly absolutely what will happen. It is not true fact because the probability says it will. It's just an estimated guess. It's a good guess. It is more likely that that will happen than the opposite, but it's still not true fact. So something to keep in mind when you're doing probability. Okay, and our exit ticket for this chapter, chapter 22. So think back to our section on data analysis, and I want you to write in your journal, what is data analysis? And then I want you to also write what is probability and explain both types. So again, write that in your journals, and that will be your exit ticket for this chapter. Thank you very much.